The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome to the channel Statistica Hub. So this is lecture number 4 of Bayesian Inference, and in the previous lecture we had discussed about truncated distributions, and I was also going to discuss mixture distribution in the previous lecture, but yeah, due to lack of time I was not able to do that. But yeah, let's discuss the mixture distributions in today's lecture, and some other important distributions also that we are going to use in further lectures. Yeah, so let's start with it. Okay, so yeah, talking about the distributions, firstly, one thing that you need to know, that we need to know, what is the central concept of statistics. Okay, so the central concept of statistics says that if I'm having a population, okay, and we have some summaries corresponding to population. I want to know basically the summaries of the population. By summaries we mean to say that what's the population mean, variance, like mean, variance, standard deviation. These are some population things, population summaries that we want to know. Okay, and these things are said to be my parameters. Okay, that is summary corresponding to population is my parameters. And to know about these parameters, what do? We firstly draw the sample from this population, and the summaries corresponding to the samples, like mean, median, like mean, variance, standard deviation, population proportions, there is correlation coefficients, all these things, these are said to be the statistics, sample statistics. So the summaries corresponding to the sample is my sample statistics, and the summaries of the population are my parameters. Now the central concept of the statistics says that if I'm on, what are the notations of them? Yeah, that is also the main thing, that the population parameters has their specific notations. That is, like if I'll talk about the mean, okay, then here the mean is denoted by mu. Okay, then the mean here is denoted by x bar, or you can say y bar, anything. It depends on you that what are you denoting a random variable, x bar or y bar. Here the population proportion is denoted by p, and here it is denoted by p cap. Similarly, here the variance is denoted by sigma square, and the sample variance is denoted by s square. Okay, and also like correlation coefficient, here it's rho and here it's r. Right, so it is sample correlation coefficient. And similarly regression coefficient, we are having beta here and we are having b here. So these are the population parameters, and these are my sample statistics. Okay, so their notations are also different, so by seeing the notation you can easily judge whether they are talking about population or sample. Okay, so my main task is to find out the population parameters. Okay, is to estimate the population parameters. So to estimate these population parameters, what do? We have a population, we draw a sample from this population, let's say of size n. Okay, we have drawn a sample of size n from this population, let's say x1, x2 to xn is my sample, and I want to estimate my population mean. Okay, and to estimate this population mean, we are finding sample mean. Okay, we are trying to estimate the population mean from sample mean. Okay, and what is my sample mean here? In n cases, that is x bar 1 upon n summation xi. But there is one thing to notice, that I cannot do this, that I am drawing one sample from a population and I am calculating the sample mean from it, and I would say that this would be my estimate of population mean. We can't do that, because if I draw another sample from this population, let's say this is sample 1 and you are drawing some sample 2 from this population, then the sample mean corresponding to that sample would be different from the previous sample, right? So if this is x1 bar and this is sample mean x2 bar, then these sample means would be different. So from this you can say that for every different samples I am drawing from the population, I will be getting different sample means. That means my sample mean would follow a certain kind of distribution, right? We are saying that for different samples, we'll be getting different x bar. Okay, that means sample mean would vary, but my population mean is fixed, right? Population mean is fixed, it would not change. Okay, so what we are saying that my sample mean would follow a certain kind of distribution. Okay, and this distribution is said to be the sampling distribution. Sampling distribution, that is distribution corresponding to a statistic. I have already told you that these are my statistics. Distribution corresponding to a statistic is basically we are finding the for the sampling distribution. Okay, so in all these portions, whether we are doing statistical inference, whether we are doing Bayesian inference, what we are doing is trying to estimate the population parameters. And to do that, we always do this. We are having a population and we draw a sample from that population. Okay, we are having a population, we are drawing the sample from that population under the assumption that the population belong to a certain parametric family of distribution. Parametric family of distribution. So we assume this thing that population has some distribution, it would belong to some parametric family of distribution. Parametric family means that it would have some parameter. We always say that population is denoted by x and it is following some normal distribution with mu and sigma square, where mu and sigma square are my parameters. So we always draw the sample under the assumption that my population would be following a certain kind of distribution. Okay, and assuming this thing, we are trying to estimate these population parameters from the sample. Because if I know my parameters, if I got the value of these mu and sigma square, then I know that my population is following normal distribution with these parameters, then I can compute any probability from it, right? We have the PDF corresponding to normal distribution, probability density function. And if I know these parameters, I can calculate the probability corresponding to n distribution. Probability x less than equals to 2, probability of any range of values, because it is a continuous distribution, we have to consider the ranges. Okay, so that goes similarly for any kind of distribution. So the thing is, population, we are saying that the population would be following a certain kind of distribution and we are estimating the population parameters from it. Okay, now what are the certain kinds of distribution that we will see under the ongoing process of Bayesian inference? There are some other like so many distributions. Some of them are discrete distributions, continuous distributions. In discrete you have Bernoulli, binomial, beta distributions, like so many distributions. Beta is actually continuous, but yeah, so many distributions we are having. And in those distributions we'll be discussing some 2 or 3 distributions here. So before talking about that, let's just talk about mixed distributions. I don't like red color. Yeah, mixed distributions. Mixed distributions. Yes, so we are using mixed distribution, or you can say mixture distribution, whenever we are taking the mixture of mixture of two or more probability distribution. Okay, let's consider an example. Let's say if you are having an insurance loss data, or you can say insurance data. Okay, and we are saying that this insurance data, it is like, I think it is valid to assume that it would follow a exponential distribution with some parameter. Okay, so we are saying that this insurance data is following some exponential distribution, but the mean of this exponential distribution, the mean of this exponential distribution would be different for different individual. How? Because insurance data is for like a particular individual. When it is taking an insurance, then from individual to individual it would vary, because depending on on an individual's salary, what would be the salary of an individual, what is its his or her lifestyle, what are expenses, and depending on certain kinds of characteristic, the mean according to for each and every individual would vary. So we are saying that the insurance data is following certain exponential distribution, and this mean of this exponential distribution would also follow a certain kind of distribution, because it is also varying from individual to individual. Okay, so for these kinds of distribution where my original data is following any distribution and the parameter of that distribution is following some other kind of distribution, it is also varying. In these cases we need mixture distributions. Okay, so talking about the origin, you can say the definition, or let's define it on a very formal way, then we are saying that let if x is following has certain probability density function f of x comma theta, where theta is actually my parameter. Okay, and we are saying that this parameter theta is following some other kind of distribution, which is g theta. Okay, and in this case, if I want to find out the unconditional distribution of x, that would be mx is equal to integration over theta f of x given theta, this would be f of x given theta, and g theta into theta. Okay, so we need to take under the consideration of the distribution of theta in these cases for finding the unconditional distribution of theta. Okay, if you have unconditional distribution of x, if you have ever like studied this before, then you must know that if my parameter is also following a certain kind of distribution, then we need to consider that distribution also. Okay, yes, now let's try to understand this concept by some example. For that, we are having certain kind of distribution. Let's talk about compound binomial. Okay, so talking about compound binomial distribution, we say that if x is following certain binomial distribution, now we know that the binomial distribution has parameters n comma theta, and we are saying that this theta, which is the probability of the binomial distribution, probability of success, this is known to us. Theta is the probability of success which is known to us. Okay, now we are saying that this n sample size is following some other distribution which is Poisson lambda. Okay, now to find out the marginal of x in this case, you could be doing m of x, that is equal to summation. Firstly, put down the binomial distributions PDF, ncx theta to the power x 1 minus theta raised to power n minus x. Okay, and n is again following some Poisson lambda. Okay, so what would be the distribution of the Poisson lambda? The Poisson lambda would follow e raised to the power minus lambda raised to the power n upon factorial n. Okay, so this is the distribution which is f of, this is, you can say, f of x given theta, that is ncx p raised to the power, not p, theta raised to the power x 1 minus theta raised to the power n minus x. and this is Poisson, which is f of theta, which is f of n, sorry, f of n, that is e raised to the power minus lambda, lambda raised to the power n upon factorial n. Okay, now we always put the limit of theta here, note it here. Okay, limit of theta, and the limit of theta here is n, basically 0 to infinity. Now I need to solve this. No, so let's take e raised to the power minus lambda. I can take lambda raised theta raised to the power x, summation n is equals to 0 to infinity. So here it becomes ncx 1 minus theta raised to the power n minus x, and lambda raised to the power n minus x. Okay, theta raised to the power x is also already outside upon factorial n. Okay, and that is further is equals to e raised to the power minus lambda, lambda theta raised to the power x, summation n is equals to x to infinity because of this power. Okay, and if I open it, factorial n upon factorial x, factorial n minus x into lambda 1 minus theta raised to the power n minus x upon factorial n, and this would cancel out. Okay, now we will be having e raised to the power minus lambda, lambda theta raised to the power x upon factorial x, summation n is equals to x to infinity, and that is lambda 1 minus theta raised to the power n minus x upon factorial n minus x. Okay, now e raised to the power minus lambda, lambda theta raised to the power x upon factorial x. Now what is this? This is the expansion of exponential e raised to the power x. Okay, so that can be written as e raised to the power lambda 1 minus theta. Okay, so by summing up all these, we will be having, let me write it on the another page. Yes, yeah, so we will be having m of x that is equal to e raised to the power minus lambda. Okay, it will be e raised to the power minus lambda theta raised to the power x upon factorial x. Okay, for x is equals to 0, 1, 2 to n. Okay, so my marginal of x is actually following Poisson distribution with the parameter lambda theta. Okay, so that's how we can find out the marginal corresponding to any mixed distribution by if I am having mixed distributions. Okay, so that is compound binomial. Similarly, you can find it out for another distributions also. Let's take into consideration one more example, that is binomial beta. Binomial beta. So if you are having binomial beta distribution, for this, let's say if your x is following binomial distribution with the parameter n and theta, and where n is known and theta is unknown. Okay, theta is unknown, and we are saying that theta is following beta distribution with the parameter a and b. Okay, now to find out the marginal corresponding to these, firstly, what will be the PDF here? Okay, that is PMF, sorry, f of x given theta, that would be ncx theta raised to the power x 1 minus theta raised to the power n minus x. And what is the PDF of beta distribution? F of theta, that will be equal to theta raised to the power a minus 1 1 minus theta raised to the power b minus 1 upon beta a comma b. Okay, so to find out the marginals corresponding to them, we will be doing the computation corresponding to these distributions. Okay, so my m of x, the marginal distribution of the x, would be equal to 0 to 1, because I know that the beta distribution ranges from 0 to 1. Okay, so we will be having ncx theta raised to the power x 1 minus theta raised to the power n minus x into theta raised to the power a minus 1 1 minus theta raised to the power b minus 1 upon beta a comma b into d theta. Okay, and doing some simple calculations, ncx upon beta a comma b 0 to 1 theta raised to the power x plus a minus 1 1 minus theta raised to the power n minus x plus b minus 1 into d theta is equals to ncx upon beta a comma b. Okay, Now what is this? This is actually the form of beta. I can write the expansion of beta. I can write it as beta of x plus a comma n minus x plus b. Okay, so this is the distribution that we have calculated for binomial beta. Similarly, you can calculate it for any distribution. You can have normal distribution. You can have binomial beta, as we have discussed. You can have compound Poisson. Yeah. So let's talk about compound Poisson. That is also a certain kind of distribution that will be used mainly. Yeah. So compound Poisson. Yeah. Compound Poisson. So the calculation would be similar to what we are doing right now. So let's say if x is following Poisson theta and theta is following gamma a comma b. Okay, so to find out the marginal, again using the same procedure, that it is from a to b. Okay, and the PDF of x first, that is e raised to the power minus theta raised to the power x upon factorial x into the gamma distributions PDF, that is b raised to the power a e raised to the power minus b theta raised to the power a minus 1 upon gamma a into d theta, which is equal to b raised to the power a upon gamma x uh, factorial x gamma a to b, that will be theta x plus a minus 1 e raised to the power minus theta b plus 1 into d theta, which is further equals to b raised to the power a factorial x gamma a, and this is x plus a upon b plus 1 to the power x plus a. Okay, that is further is equals to b raised to the power a gamma x, that will be factorial a minus 1, and this will be factorial x plus a minus 1 and b plus 1 x to the root to the power x plus a. Okay, so this can be written as x plus a minus 1 c a minus 1, and by distributing it we will be having b upon 1 plus b to the power a and 1 upon 1 plus b to the power x. Okay, now I can rewrite this thing as, let me write it here, x plus a minus 1 c a minus 1. So whenever I can see that I can make certain kind of distribution, we'll try to make it. Okay, b upon 1 plus b to the power a, and now I can write this thing as 1 minus b upon 1 plus b to the power x. Okay, for x is equals to 0 1 2 going on. Now I can see that this distribution is actually negative binomials PDF. Okay, so this is negative binomial PDF, so my marginal of x in this case would be negative binomial with the parameter a comma b upon b plus 1. Okay, so yeah, simultaneously discussing about the mixed distribution, we have also talked about Poisson distribution, negative binomial, and yeah, some basic like what will the PDF of them look like. Okay, beta distribution, all these things. Okay, now here let's talk about this gamma a comma b. Okay, yeah, gamma a comma b. Yes, so when I have talked about this distribution, that x is following certain kind of distribution gamma a comma b. Okay, we know that I'm having this kind of distribution. So what is the domain of this distribution? Domain is basically x belongs to 0 comma infinity. Okay, now the PDF corresponding to it, the PDF is b raised to the power a x raised to the power a minus 1 e raised to the power minus b x upon gamma a. Okay, what are the parameters? Parameters are a greater than 0, b greater than 0, where a is the shape parameter and b greater than 0 is a rate parameter. Okay, now the mean and variance corresponding to it, expectation of x is a by b and the variance corresponding to it is a by b square. Okay, now I am discussing this distribution because sometimes we also write the PDF corresponding to it as f of x, that is equal to 1 upon gamma a beta raised to the power a, x raised to the power a minus 1, e raised to the power minus x by beta. Now what is the difference between these two parameters? The only difference between these two distributions, the two formation of, they are the same distribution. This is also gamma a comma b, this is also gamma a comma b, but there is a very slight change, or you can say slight difference between these two distributions. Here I am having the parameter as a greater than 0, which is shape parameter. Similarly here I am having the a greater than 0 parameter, which is shape parameter. Okay. Here I am having b greater than 0, which is rate, but here I am having beta. Okay, where beta is actually a scale parameter. Okay, beta is also greater than 0. So rate and scale are inversely proportional to each other. You can say b is equal to 1 by beta. Beta is a scale parameter and b is a rate parameter. So b is rate. So whenever they are writing the distribution into this format, that means they are taking beta as a scale parameter, and whenever they are writing b into the denominator, right, they are writing it as a rate parameter. So depending on that, they change the distribution, but they are actually inversely proportional to each other. Okay, and yeah, and we know that if I put a is equals to 1, okay, this would give me exponential distribution. Exponential distribution. Okay, because if I put a is equals to 1 here, you can see I will be getting f of x is equals to b e raised to the power minus bx, that is actually exponential with the parameter b distribution. Okay, now one more thing that you need to know about it, that the important thing is that if as a increases to infinity for any given value of b, then the gamma distribution, then the PDF of gamma would approaches to normal. Okay, for any fixed b, for any given value of b, if a is increasing to infinity, then the PDF would approach to normal distribution. Okay, so yeah, that is something important regarding gamma distribution that we need to know. Now there is one more thing in the gamma distribution, which is inverse gamma. Okay, inverse gamma distribution. So when x is following inverse gamma. Now as we have discussed about gamma distribution, the same scenario goes for the inverse gamma distribution. Okay, in the inverse gamma distribution, we are saying that if y is following certain gamma a comma b, okay, then x is equals to 1 upon y. If I am having the transformation like this, x is equals to 1 upon y, then only my x is following inverse gamma distribution. Okay, inverse gamma with the parameter a comma b if my y is following gamma a comma b. Okay, now same thing, what will be the domain? Domain would remain same, that x belongs to 0 to infinity. Okay, the PDF, because of the transformation, you can use the transformations of one dimensional variable here to get the PDF here, but yeah, I will tell you directly that it will be b raised to the power a gamma a x raised to the power minus a minus 1 e raised to the power minus byx. As similar to gamma, you are having the parameters which are same, a greater than 0, which is your shape parameter, and b greater than 0, which is your rate parameter. Okay, and other things like what would be the mean and variance corresponding to it. The mean here is b upon a minus 1 for a greater than 1, and the variance is b square upon a minus 1's whole square a minus 2 if a is greater than 2. A is greater than 2, and as we wrote, if I wrote this PDF according to scale parameter, then sometimes you can also see the inverse gamma into this format, as we see in the gamma distribution, that is 1 upon a b to the power a x raised to the power minus a minus 1 e raised to the power minus 1 by bx, where b is denoting the scale parameter and here b is denoting my rate parameter. Okay, so depending on these, my inverse gamma distribution, this is my inverse gamma, and this is my gamma distribution. Now let's talk about one more important distribution that is, I think, used everywhere in the statistics, which is a part of continuous distribution, that is normal distribution. Okay, so talking about the normal distribution, or you can say also the Gaussian distribution, X is following normal with the parameters mu and sigma square. These are the parameters. Okay, the parameters mu and sigma square is greater than 0. Okay, the domain of this distribution is from minus infinity to infinity, and the PDF goes from 1 upon sigma root 2 pi expectation of minus 1 upon 2 x minus mu by sigma's whole square. Okay, the mean is mu and the variance is sigma square. Now normal distribution is a symmetrical type of distribution, so as we know that if it is a symmetrical distribution, then the mean, median, mode are all equal. I know my writing is too bad. Mean is equals to median, that is equals to mode. Okay, now if I let's see the graph according to it. If for a symmetrical distribution, I will be having a graph like this, and it's a bell-shaped graph. Okay, and for a fixed value of mu, let's say normal 5 comma 4. Okay, if not for normal 5 comma 4, if I'm having a graph like this is my 5. Okay, and 4 is the variance corresponding to it. And for a fixed value of mu, if I change the variance, let's say it is now 0.5 whole square. Okay, then the graph would be like this. Okay, because the variability actually only changes the spread of the graph. The mean would be same for both of these cases. 0.5 whole square, not its overall whole square. Okay, yeah. Okay, so yeah, this is about normal distribution, that the center would not change, the variability actually changes if I change the variance, the spread would change of the normal distribution. Okay, now let's talk about standard normal. Okay, that for z, which is equals to x minus theta by sigma, okay, then this would follow normal 0 comma 1, where mean is 0 and variance is 1. Okay, that is my standard normal distribution. Okay, and the distribution corresponding to the standard normal, you can just put the value of 0 and where 1 in my original PDF, and you will get the PDF of this new distribution, that is 1 upon root 2 pi e raised to the power minus z square by 2 for z lying between minus infinity to infinity, and that is my standard normal distribution. Okay, and yeah, these are some properties, that if you are having x1, x2 to xn, which are independent random variable, okay, each of these xi's are independent random variable, and each of them is following normal distribution with the some parameter theta k and the variance sigma k square, then the sum of these independent random variables would follow normal distribution with the sum of means k is equals to 1 to n theta k, and the sum of variance 1 to n sigma k square. Okay, this is the sum of parameters when sum of independent random variables. Okay, yes, now let's talk about some other property, that if you are having x1, x2 to xn, which is a random sample, if x1, x2 to xn is a random sample from normal distribution with the mean theta comma sigma square. Okay, and what will be the sampling distribution of sample mean? X bar. So x bar, we know that x bar is follow 1 upon n summation xi, and it is already saying that my population is following a normal distribution with the parameter theta comma sigma square. Then I don't need to check whether the sample what will be the distribution of a sample, because the sample has been drawn from this population only. So I will just directly say that my sample would follow the normal distribution. But my main concern is that what will be the distribution. X bar would follow normal distribution, but what would be the mean and variance corresponding to it? Okay, so to find out the mean and variance corresponding to it, we can just use the some simple calculations. That what will be the expectation of X bar? That would be expectation of 1 upon n summation xi, which is 1 upon n summation expectation of xi. Now here xi is basically is going to from 1 to n, because I have drawn n random samples, that is equals to 1 upon n. Now these are n independent random samples, right? So that is n into mu, n into theta, sorry, because I am having the expectation of xi for all of them as equals to theta. So theta. Similarly, you can check for variance of x bar. Variance of 1 upon n summation xi. Now we know that the property corresponding to variance, if a constant has been multiplied to a variance, then it would come out as a square. So that is 1 upon n square summation variance of xi. That is equals to 1 upon n square. Now I know that the variance of each of the xi's is n square, so n sigma square, so sigma square by n. So from this we can say that the x bar sampling distribution of x bar is actually normal distribution with the mean theta and the variance sigma square by n. Okay, so that's how you can find out the sampling distribution corresponding to any kind of statistics that you are going to face. Okay, now let's talk about bivariate normal distribution. Okay, bivariate normal distribution. Okay, so in the bivariate normal distribution we have we have two random variables and we have 5 parameters. Okay, so we are saying that x comma y is following joint distribution of normal, is following bivariate normal distribution with 5 parameters. And what are these parameters? Mu x, mu y, sigma x square, sigma y sigma y square, comma rho. Okay, for these 5 parameters are basically mu x, mu y, sigma x square greater than 0, sigma y square greater than 0, and the correlation coefficient which belongs from -1 to 1. Okay, so these are my 5 parameters, and the PDF corresponding to them, f of x comma y, that is equals to 1 upon 2 pi sigma x sigma y root 1 minus rho square, expectation of -1 upon 2 1 minus rho square, x minus mu x upon sigma x is whole square, plus y minus mu y upon sigma y is whole square, minus 2 rho x minus mu x by sigma x and y minus mu y by sigma y. Okay, that is the PDF corresponding to it, where if I am having a joint distribution which is following bivariate normal, then the marginal distribution corresponding to x would follow normal distribution with the mean mu x and the variance sigma x square, and the marginal distribution corresponding to random variable y would follow normal distribution with the mean mu y and the variance sigma y square. Okay, these are the marginals corresponding to x and y. Okay, now there are some certain properties corresponding to these bivariate normal distribution that we should know, that the conditional distribution of y given x, okay, that y given x would follow normal distribution with the mean mu y plus rho sigma y upon sigma x, x minus mu x, comma sigma y square 1 minus rho square. Okay, and in this case if we are talking about the standard normal distribution, okay, what will be the standard bivariate normal? Okay, the standard bivariate normal distribution, basically I'm going to say that the mean is equals to 0 in the standard normal case and the variance is going to be 1. Okay, so if I am having these two equations, if I put these values in my PDF here, then we will be getting standard normal distributions. Okay, now if I am having a standard bivariate normal distribution, then at this case the conditional distribution would actually be equal to normal rho x, because this would be 0, these would be 1, right? This would be 0 rho x comma 1 minus rho square. Okay, and if you can say, if correlation is 0, if correlation is also 0, then your y given x would follow. If correlation is 0 in this case, then this would follow normal mu y comma sigma y square. So basically at this case you are having marginal of y if the correlation is 0. Okay, so these are some properties corresponding to conditional bivariate normal distribution, and we have already discussed the normal distribution, the standard normal. So that was all about the distributions, the important distributions, and yeah, there are some other distributions also, like beta distributions, um, Pareto distributions, Weibull distributions. Yeah, but we'll see these kinds of distributions as we go on with the binomial discussions. So I think that's enough for the today's class, and in next class we will be discussing about frequentist and Bayesian approaches, and also the Bayesian framework. That how does the Bayesian framework works, and what is the difference between these two kinds of approaches that are used widely for estimating the parameters. Okay, okay, so let's meet you in the other lecture. Thank you for today's class.